Hi everyone, welcome back to Nuclear Physics for Dummies. I'm Mert, and in episode 1, we zoomed into the nucleus and talked about its structure and properties. Today, we will talk about something even more fundamental. What holds the nucleus together? Why are some nuclei stable and others not? Here is the key idea. When you put protons and neutrons together to form a nucleus, the whole thing weighs less than the sum of its parts. That missing mass, we call it the mass defect. And it shows that some of the mass was converted into energy to hold the nucleus together, thanks to Einstein's famous formula E equals mc squared. We call that energy the binding energy. The amount of energy you would have to supply to break the nucleus apart into individual nucleons. If we take the equation E binding energy equals delta m, because we have a change in mass, times the square of the speed of light c, and delta m here would be representing the mass defect. Free nucleons would have the total mass of m free. Bound nucleus mass would be equal to m free minus mass defect. It's one of the most important quantities in nuclear physics, and we can even measure it directly in experiments. For most stable nuclei, the binding energy per nucleon, that is per proton or neutron, is about 8 megaelectron volts. It's not exactly constant though. It depends on the size of the nucleus. If we plot binding energy per nucleon versus mass number A, here is what we see. For very light nuclei, adding more nucleons increases binding. The nucleus becomes more stable. Around atomic mass number A60, like iron, the binding energy peaks. That makes iron 56 the most stable nucleus in nature. Actually, nickel 62 has slightly higher binding energy per nucleon, even a bit better than iron 56. But iron 56 is much more abundant and commonly cited as most stable. For very heavy nuclei, the binding energy per nucleon decreases slightly. That's because the protons start to repel each other more due to the long-range Coulomb force. This binding energy curve also explains why we can get energy in two ways. By fusing light nuclei, which increases binding energy and releases the excess energy. Here is a very commonly used example of a fusion reaction where deuterium and tritium fuse to create helium and releases a neutron. Or by splitting heavy nuclei, called fission, which also results in more tightly bound pieces and releases energy. Here I'm drawing how the fusion reaction occurs. A heavy nucleus like uranium-235 absorbs a neutron. This makes it unstable. It splits into two smaller nuclei plus some extra neutrons and releases a lot of energy. The extra neutrons can then hit other nuclei and cause more fission. This is called a chain reaction. That's why both fusion and fission can power stars and nuclear reactors. But there is more. Experiments show that certain numbers of protons and neutrons make nuclei especially stable. We call these the magic numbers. They're 2, 8, 20, 28, 50, 82, and 126. When a nucleus has both a magic number of protons and a magic number of neutrons, we call it doubly magic, like helium-4 or calcium-40. These are particularly stable compared to their neighbors. Another way we measure stability is through separation energy, the energy needed to remove one neutron or one proton from the nucleus. When that number gets close to zero, the nucleus is unstable and can spontaneously emit nucleons. Beyond a certain point, called the neutron or proton drip line, adding more neutrons or protons just doesn't work anymore. But here's a fun fact. Just because a nucleus is beyond the drip line doesn't mean it disappears instantly. Some of them can live surprisingly long before decaying. These ideas, binding energy, magic numbers, drip lines, also explain how elements are created in stars and supernova. When we talk about nuclear reactions, one of the first questions we ask is, how likely is this reaction to happen? We answer that using a concept called cross-section. Here is the idea. Imagine the nucleus as a tiny target. When you shoot a particle like neutron or an alpha particle at the nucleus, it can scatter off, react, or just pass through. The cross-section tells us how big the target area appears to the incoming particle. In other words, the probability of a reaction. We actually measure it in units of area. And because the numbers are so small, we use a special unit called the barn, where 1 barn equals to 10 to the power of minus 28 square meters. The cross-section determines how open reactions happen in nuclear reactors, in stars, or in particle experiments. If the cross-section is large, it means the nucleus is a good target. Reactions happen often. If it's small, the nucleus is harder to hit or less likely to react. Experimentally, we shoot a beam of particles at a thin target and count how many react or scatter. We then compare that to how many particles hit the target in total. This ratio gives us the cross-section, and we can measure how it depends on the energy of the incoming particles. Not all reactions are the same. In elastic scattering, the particle bounces off and the total kinetic energy stays the same. In inelastic scattering, some of the kinetic energy is used to excite the nucleus or create new particles. We can even measure the differential cross-section, which tells us not just how likely the reaction is, but also what angles the particles scatter at. Cross-sections help us figure out the size and shape of nuclei, the density of protons inside the nucleus, how reactions power stars, nuclear reactors, and even medical isotopes. For example, by studying how alpha particles scatter off a nucleus, we can even estimate the size of the nucleus, just like Rutherford did in his famous gold foil experiment. So to sum up, cross-section is a simple but powerful way to describe how likely a nuclear reaction is, and it's the foundation for much of experimental nuclear physics. Thanks for watching, don't forget to like and subscribe, and I will see you next time on Nuclear Physics for Dummies.